Let's get started. My name is Noemi Duran, and I'm going to be the instructor of this webinar series. I'm going to quickly introduce myself for those of you who don't know me. I'm a biologist and an educator. I studied biology at the University of Valencia in Spain, where I specialized in zoology and social environmental education. Later, I completed my doctorate in marine biology at Loma Linda University in California. I have worked as a secondary school teacher and a university professor, as well as a non-formal educator in zoos. And 5 years ago, I became the director of the European branch of the Geoscience Research Institute, or the GRI for friends. For those of you who don't know the GRI, it is the Scientific Research Institute for the Seventh-day Adventist Church, and it oversees the study of the relationship between faith and science, especially in the area of origins. If you want to know more about the GRI, you can check out the grisda.org website. There are those who believe that religion and science are two fields that are opposing and incompatible, but at the GRI, we believe that it is the exact opposite. We believe that God is the author of both the Bible and nature. Therefore, faith and science are closely related. And that's the reason for this webinar series, to share with you the reasons why we defend this idea. I'm sure that you have experience in discussing or arguing about this topic with other people who have a different vision. And that's probably why you're here. But I would like to start with an important message. This is a very complex and very broad field that has an infinite span of information. I have been studying and training in this field for 15 years, and I'm still learning new things each day. So, just to let you know, I do not have all of the answers, and even if I did, I wouldn't have time to give them to you in such a short amount of time that we are going to be together during this series. As the name of the series says, this is a basic course in which we are going to cover the fundamentals of the most common topics. For those of you who may want higher level of information, I will provide information or material that you can consult, and if you are interested, we can organize an advanced course for later on. This basic course is structured into 3 modules with 4 topics in each module. Today we are starting the first module, Science, with the topic, What is this thing called science? We will do the following in each session. The presentation of the topic will last about 25 minutes, and then we will dedicate between 10 to 15 minutes to answering questions that you can send anytime during the presentation through the available question and answer button at the bottom of the screen. One more thing. Before we dive into this topic, because we have participants of several languages to make the communication as easy as possible, the presentations that you will see on your screen, the text, will be in English, even though I will read them in Spanish. And our wonderful translators will read them in their corresponding language. I want to take the opportunity to thank our translators for their help and their effort. We have Lisa Decker in English, Dante Germán in German, Laurentio Drugo in Romanian, Antonia in Búlgaro, Italiano, and Diego Costa in Portuguese. And thank you so much to all of you. Let's start today's topic, but before, I'd like to start with a prayer to ask God to accompany us during this session. Dear Lord, we want to thank you because you are a great creator, and you show us every day that you love us and care for us. We ask that you help us to learn as much as we can today and grow closer to you. In your name, amen. What is this thing called science? I borrowed the topic or the title of this topic from the book by Alan Chalmers. I read it for the first time when I was a teenager, so it's not a recent book, but it's very interesting, and if you haven't read it, I would recommend it. We'll talk about him a little bit later. We all have an idea of what science is. When you think about science, you may imagine something like this: someone wearing a white lab coat, mixing dangerous substances in a laboratory. Or maybe you relate science to a giant chalkboard full of complicated formulas and calculations. It's also possible that science may sound more like sophisticated machines like particle accelerators or radio telescopes. But all of these things have to do with science. But what is science? The word science can simply mean knowledge, but a more comprehensive definition would be the following: the intellectual and practical activity encompassing the systematic study of the structure and the behavior of the physical and natural world through observation and experiment. I like this definition a lot because it's pretty complete. It starts out by saying that science can be a theoretical intellectual activity or something applied practical. It also tells us what the object of study of science is, the physical and natural world, and what we want to learn from it, which is both its structure, what it's like, and how it behaves, how it functions. And lastly, at this very important, it specifies the scientific work method. It talks about a systematic way of study that uses the tools of observation and experimentation. We could say that this science is a human attempt to obtain knowledge about the world, about nature. But it's not the only one. There are other sources of knowledge, but what makes science different, it characterizes it precisely, is its methodology. I'm sure that you have studied at one point, or have at least seen somewhere, a diagram similar to this one that represents the so-called scientific method. Although this diagram has been tremendously simplified, and many current scientists agree that science doesn't actually function this way, it will serve to explain the difference between science and other sources of knowledge. We start with an observation, which then generates a question. Then we come up with a possible answer to that question, which is what we call a hypothesis. And then the next steps consist in proving if this answer is possible, if this hypothesis is correct or not. So far, there's not much difference with other sources of knowledge. Philosophers and theologians also ask questions. They also suggest possible answers, and they try to find out if their answers are correct. The difference is the way you check the veracity of the hypothesis. Science tests its hypotheses through observations and experiments. It uses empirical evidence, what we can perceive with our senses, what we can see, hear, touch, measure. If the result of the experiments, if the empirical evidence supports the hypothesis, then it is accepted as valid. If the evidence denies the hypothesis, then it is refuted and a new one is proposed and we start again. Or at least this is what the theory says. In case the philosophy or religion, the way of proving that an answer is valid is different. Philosophy supports logical reason. We use the mind and reasoning to reach a conclusion based off of certain premises. In the case of religion, to prove that an answer is correct, it is compared to the source of authority that many Christians believe is the Bible. If the answer matches what the Bible says, then it is true, and if not, then it's false. Also in theory. Do you know why science is so successful in our society? In part, it's because of all the advances and improvements that we have obtained thanks to it. But I believe that it also is because of the scientific method that we just explained in our instinctive way of learning. Children, even from very little, use the sequence of observation, question, hypothesis, experiment. We can see that here in this scene. A baby observes a small object that is moving on the floor and thinks, could this be food? And then it puts it in its mouth to empirically check if it is food. Let's look at another everyday example that is a little less gross or disgusting. Imagine that you wake up in the middle of the night. You flip the light switch from your bed, but the light doesn't turn on. You ask, what's going on? And then you come up with an answer. The light bulb must have burned out. So then you flip the switch of the lamp that is on your bedside table, and it doesn't turn on either. Incorrect answer. You look for a new hypothesis. The fuses must have blown out. You get up and use your phone as a light to walk to the fuse box in the house. Everything is correct. So that's not either. Has the electricity gone out? You go over to the window and see that the other houses don't have light and the street lamps aren't working either. Mystery resolved. The scientific method seems natural to us and we unconsciously use it at all times, which is why we consider it a good way of resolving problems. Perhaps even the best way, because it's based on something objective. What we can see, touch, measure, and test. The problem arises when we leave the everyday environment and go to a scientific environment where everything is much more complicated. Many of the questions that scientists ask cannot be resolved with simple experiments with obvious results. Take, for example, a very current question. What would the consequences for life on Earth be if the average temperature were to increase by 2 degrees? Let's suppose that our hypothesis is that life on Earth will be extinct. Obviously, our experiment cannot be to increase the temperature of the planet by 2 degrees to see what happens. But what we can do is a small-scale experiment. We will fill an aquarium with corals, fish, and many marine invertebrates. And when the ecosystem is working in a balanced way, we increase the temperature of the water by 2 degrees. Putting aside the moral dilemma of using or not using animals for experiments, we can be sure that what happens in the aquarium is the same thing that would happen in the ocean. If all the fish die, does that mean that all marine animals would die? We could also observe natural ecosystems, like a coral reef, and how it is affected by an increase of temperature in the sea, which is approximately 0.1 degrees. And try to calculate what would happen if it were to increase by 2 degrees. But how do we know if our calculations are correct? What I'm trying to say with this is that science is real. We're going to be repeating this over and over again throughout this whole webinar series. And in the book by Hugh Gauch in his year 2000, Scientific Method in Practice, it says, every conclusion of science, once fully disclosed, involves components of 3 kinds: presuppositions, evidence, and logic. And this is precisely the fundamental concept for today and for the rest of the series. Because science isn't always about empirical evidence. We also associate to other sources of knowledge. But for right now, we're going to concentrate on the relationship between evidence and data. What we were able to measure, photograph, look at, take notes about. But like we've said, this data doesn't always, or the experiments don't always create the phenomena that we expect to see. And that's where logic enters. And that's when we take the data, the evidence, and make interpretations. And this is fundamental. And I'm going to be telling you today and during the rest of this whole series between data and interpretation. I'm going to use an example that I always give my students. What is the difference between these two sentences? Brazil is the soccer team that has won the world championship the most times. Or Brazil is the best team in the world. I'm sure that you have all realized that there is an important nuance between these two statements. The first is an objective fact. We can look at the records of the World Cup soccer results and check. The second statement can be considered a logical conclusion from the first. But it's still a subjective opinion that depends on the criteria by which we define the best team in the world. The first sentence is data. The second is interpretation, the conclusion. In this case, it's easy to see the difference, but sometimes in science or scientific literature, it is more difficult to detect what is data and what are interpretations. And as we said that this is going to be very important, we're going to take a few minutes to practice this, to see the difference between data and interpretation. With a few sentences, simple sentences. And then we'll do an analysis on an actual scientific article. I will give you a few seconds to decide whether it is data or interpretation, and then we'll move on to the correct answer. So the first sentences in this series. A water molecule is made up of 2 hydrogen atoms and 1 oxygen atom. This is data. Most of you or all of you probably thought that this is data, even though we cannot actually test this with our senses because we can't see atoms. We can't test it with anything. They're so small. But at present, we call this empirical evidence, and it's considered not only what we perceive directly, but also the information that we can obtain with machines or tools that expand our perception, such as microscopes, telescopes, and other laboratory machines. Water is essential for life. I'm sure that some of you thought that this is data, but such a broad statement is difficult to prove empirically. Can we be sure that there is no type of life in the universe that does not need water? So that makes it an interpretation. To convert it into data, we would have to confirm the statement by saying, for example, water is essential for all known living creatures. This is data because we know this. We've tried it and we've tested it. And now I'm going to tell you a little short story, and we're going to stop at different sections and see if they are data or interpretations. John and Mary ate at a restaurant last night. This is data. We can ask them directly, we can look at the cameras in the restaurants. Last night, John felt very sick and was brought to the hospital. This is also data. The food John ate at the restaurant made him sick. You've probably already seen that this is interpretation. This is a very common type of interpretation. It is called causation. It takes two pieces of data that appear together, or one right after the other, and concludes that one is the cause of the other. But in science, it's very important to remember that just because two pieces of data are associated together, it doesn't mean or imply that one is the cause of the other. Let's continue. John, Mary, and 14 other customers of the restaurant were hospitalized last night. This is also data. Spoiled food at the restaurant made the customer sick. Is this data or interpretation? Don't look at the picture. If we only have the information from the sentence, we should continue considering this as interpretation. But if they've actually taken a sample of the food from the restaurant and seen that it contains toxins or pathogens, then we can consider it data. In either case, I use this example to point out that not all interpretations are the same. It does not carry the same weight to assume that the food was spoiled when there's just one sick person, as to when there are 16 sick people who ate at the same restaurant. The first interpretation carries less weight than the second one. But even still, it could be a mistake, because maybe, or perhaps it wasn't the food but the water, or maybe the air of the restaurant was contaminated. Let's change the story. On Monday, after the rain, there were snails on the streets of my town. It's data. On Monday, after the rain, there were millipedes on the streets of my town. Also data. Rain makes snails and millipedes go out on the streets. So I'm sure that you realize that this is an interpretation, and more specifically, causation, which is saying that the rain is causing the animals to go out to the streets. All kinds of bugs go out after the rain. This is an interpretation, but it's a different kind. It has to do with generalization. We have data from two different kinds of invertebrates, or bugs, and then we extend the conclusion to all kinds of invertebrates or bugs. Let's move on to the last story. My newborn niece gained an average of 200 grams per week during her first month. This is data. We measured her weight and calculated the average to summarize all of the data in just one. Newborn babies gain an average of 200 grams per week during the first month of life. This is interpretation. It's also another example of generalization. We had information from one baby and generalized it, making it the same information for all babies. Last sentence. When my niece is 10 years old, she will weigh 100 kilograms. Clearly, this is an interpretation, and even now, we know that it's wrong. But let me explain where this outrageous number came from, because I obtained it from some data and that I took from some mathematical calculations that I did. I started with the weight of my niece when she was born, 4 kilos. I then added 200 grams each week during 10 years, and the result is 100 kilograms. This type of interpretation is called extrapolation. It consists of taking limited data in time or space and extending it outside of the study framework. Extrapolation is used quite a bit in science, and it can be very dangerous It could be very dangerous because it appears to be more reliable because you're using mathematical calculations. But in this case, we all realize that this is wrong because we know other 10-year-olds and we know that they normally do not weigh 100 kilograms. But imagine that instead of a human child, we were talking about dinosaurs or other things that we cannot prove. Okay. Now, after these practical exercises, we are going to analyze a real case from a scientific news piece that appeared in numerous scientific magazines and websites in 2017.
Ranas prehistóricas gigantes que comían dinosaurios, según afirman los científicos.
Giant prehistoric frogs that ate small dinosaurs, claim scientists. When we read this headline in a popular science publication, we assume that it must be true, because it is a scientific news. We understand that they are communicating data, or in any case, weight-bearing interpretations. What kind of data do you think this headline is based on? What data have the scientists used to affirm that giant prehistoric frogs ate dinosaurs? Since it's telling us about a prehistoric animal, then most likely the scientists have found fossils of these giant frogs, right? Exactly. It was identified in 2008 after finding fossilized bone fragments in Madagascar, a new species of frogs that they called the devil frog, or Beelzebufo ampinga. According to the reconstruction of this frog, it measured 41 centimeters and weighed 4.5 kilograms. In this image, we can see the blue fragments that were found and the reconstruction of the animal skeleton. Let's make sure that this is all clear. For what we know of the giant frog, what is data and what is interpretation? I will give you a few seconds to think about it. Here's the picture a little bit bigger so you can see it. The fossils that they found, the blue part, in the data are the data. Everything else, the skeletal reconstruction, the size and weight, and the pictures of what the frog would look like, are all interpretations. This doesn't mean that they are false or incorrect, but it is important to know that they are not things that have been measured or observed, but they have been calculated using logic and assuming that the ancient frogs are similar to current frogs.
Pasamos a la segunda parte del
Let's move on to the
titular, que
second
dice
part of
que
the
estas
headline
ranas
that says
comían
that these
dinosaurios.
frogs ate dinosaurs.
¿Qué tipo de datos
What kind
puede
of
llevar
data
a los
can lead
científicos
scientists to
a
claim
afirmar
something so
algo tan
specific?
específico? Seguramente será
It
porque
must
han
be
encontrado
because they have
restos de
found dinosaur
dinosaurios y
remains
descubierto
inside of the
restos
frog
fósiles de las
fossils,
ranas, o porque han
or
encontrado
because they have found
marcas de
frog bite
mordedura de
marks
rana
on dinosaur
en los
fossils,
fósiles de dinosaurio, ¿no?
right?
Bueno, pues no.
Well, no.
Si leemos la noticia,
If we read the
vemos que la
article, we see
investigación
that the
no se ha
research
llevado a
has
cabo
not been
con
carried out with
fósiles,
fossils,
sino con
but with
ranas
current
actuales.
frogs.
Resulta
It
que las
turns
ranas
out
fósiles
that the giant
gigantes,
frog fossils
los huesos,
the
son
bones from this
parecidos
frog
a los de un
are
tipo de
similar
rana
in
actual
shape to a
que se llama rana
certain
cornuda,
kind of
que es mucho más
frog
pequeñita.
from today. It's much smaller.
Aquí podéis ver una fotografía. Son ranas redondeadas.
It's
Tienen una
called the
boca
horned
muy
frog.
grande, son muy
They have a rounded
agresivas, se
shape
lo
and
comen
they have a very
todo.
big
Aquí veis
mouth
a
and they are
esta
very
comiéndose un
aggressive.
pez y
They
por eso
eat
se les
everything,
llama
which is why they are
ranas
known as a
Pac-Man.
Pac-Man frogs.
Bueno, pues lo que hicieron los
The
investigadores
researchers
es
used
tomar
small
estas
horned
ranas
frogs,
cornudas pequeñas
which have a head
que
width
tienen
of
la
about
cabeza
5
de más o
centimeters.
menos 5 centímetros, un ancho de cabeza de unos 5 centímetros, y con un
And they
aparato
used a special
especial
device like the one
como
that you see in
este
the
que veis
photograph
en
to
la
measure the bite
fotografía,
force of these
midieron la
frogs.
fuerza, las ranitas se enganchaban ahí y
They would
midieron
bite
la
onto it
fuerza
and
de
measure how
mordida de
strong
estas
their bite
ranas.
was.
El resultado medio
The
fue
result
de
turned out
30
to be an
newtons,
average of
que es
30
bastante
newtons,
para una rana.
which is
Es el
pretty strong for a
equivalente más o
frog.
menos a unos 3 kilos.
It's an
Pues bien,
equivalent of about 3 kilograms.
eso,
Well,
la fuerza que hacían las ranitas
the strength that
al
the
correr
frogs
son
made,
los únicos datos que
these
se
are the
midieron en
only
el
data that were
a
measured in
partir
this
de ahí,
experiment.
lo que hicieron los investigadores
From there,
es
the
calcular,
researchers
hacer
made
cálculos de
proportionality
proporcionalidad
calculations
según el tamaño,
according to size,
que para que nos
something
entendamos,
similar to
es
the
algo
rule
como
of
una regla de
3,
3, pero más
but more
sofisticado,
sophisticated.
de la ranita pequeña y su fuerza pasar a la rana grande y
And they
calcular
came
su
to the
fuerza. Y
conclusion
llegaron a la conclusión de que la
that the bite
potencia
force
de
of the
mordedura de
giant
las ranas
fossil
gigantes
frogs
fósiles
would
sería
be
de
2,200 newtons,
que es el equivalente
which is like the bite of a
fuerza
wolf.
de la mandíbula de un lobo. Entonces, al llegar a la conclusión
When they reached the
de que las
conclusion that the
ranas
giant
dientes
devil
grandes
frog
estas
could
pueden
bite
morder
as
tan
hard
fuerte
as a
como un
wolf,
lobo, los
the
autores
authors
del
of the
estudio
study
empezaron a
asked,
preguntar, ¿qué tipo de presas se
well, what
comían?
kind of prey
Y
would they
por
eat
las
then?
capas de roca en las
And
que se habían
because of
encontrado
from the
los
layers
fósiles,
of the rock in which the
dedujeron
fossils were
que eran
found, they
contemporáneas,
deduced
que
that they
vivían
were
al mismo tiempo que
contemporary.
los dinosaurios.
It's
Y
a
por lo
contemporary
tanto
animal that was
pensaron
found
que
during the same times
quizás
as the
se
dinosaurs, and
podían
therefore
comer a las
they
crías
thought
de
that
los
maybe
dinosaurios.
they would have eaten baby dinosaurs.
Los datos reales
Let's
del
review.
estudio son
The
los
actual
fósiles
data from the
incompletos
study
de las
are
ranas
the
gigantes
incomplete fossils
y,
of the giant frogs
y la
and the
medida
bite
de la
force of the
fuerza
small
de
horned
mordida de
frog.
la rana cornuda pequeña. Solo eso. Y
Just
a
this.
partir de esos datos
And from
se
there,
ha aplicado
they applied
generalización
generalization
para
to
reconstruir la rana
reconstruct the
fósil
fossil
a
frog
partir de las ranas actuales y, y
using the little
extrapolación
information they
para
have,
calcular
and
la
extrapolation
fuerza de
to
mordida.
calculate its bite
Con
force.
los datos de la pequeña calculamos la grande. Finalmente,
And finally,
a la
with
última parte,
their
a la idea de que
suggestion
comían
of what they
dinosaurios,
ate
esa parte
and
la
the
llamamos
supposedly strong bite force that they called
¿Qué
this
es lo que aprendemos?
speculation.
Que los
What have we
científicos
learned
nos
from this?
engañan, que la ciencia
The
no es
scientists
fiable,
deceive us and that science is
que
not
la
reliable,
ciencia debería basarse solo en los datos,
that science should be
basarse en
based only on
interpretaciones.
data and not interpretations? Well, no,
Ninguna de las dos cosas.
neither of the two.
Para hacer ciencia hace
To do
falta
science,
tanto
you
los
need
datos
both
como
data
la interpretación.
and interpretation.
Si la ciencia solo se basara
If
en
science
los
was
datos,
based only
los
on
estudios
data,
científicos
then
serían una
scientific
lista
studies
larguísima
would just be a
de
list of
números y
numbers and
observaciones
observations
sin llegar a
with
ninguna
no
conclusión.
conclusions
Y no
and would
servirían
all
para nada.
be useless.
Los científicos no nos engañan.
Scientists
Los
don't
científicos
fool
hacen
us.
su trabajo.
Scientists do their
Proponen
job.
hipótesis,
They
obtienen
propose
experimentos,
hypotheses,
analizan
carry
los
out
resultados de
experiments,
esos
analyze the
experimentos
results of
y
said experiments,
interpretan
and interpret
los
them,
resultados, llegando a conclusiones
reaching to
que, después de ser
conclusions that are later
revisadas y
published in
evaluadas por otros
scientific
científicos,
journals.
publican en revistas especializadas. Tengo que reconocer que
I
he hecho
have
un
to
poquito de
admit that I
trampa,
cheated a little bit
¿vale? Porque con la
because
historia esta de las
the topic
ranas
of the
no
frogs
os
was
he
not taken
enseñado
from
el
a
artículo
scientific journal.
científico que se publicó en una revista seria, en Nature, sino la noticia de
But
una
from a news
página
article
de
that
referencia
appears on a
especializada.
scientific website. Scientists are often much more cautious than journalists who are only looking for a headline that will attract attention. For those of you who are curious, I will share the link here of the original article. You will see that the title is much less attractive than the news article, and that even though the authors mention all of the interpretations that we've already commented on, that they're clearly specific, that they are merely extrapolations. With regard to eating dinosaurs, it says exactly this. Considering that bite force, the large specimens may have been able to feed on a wide variety of contemporary animals, including small crocodiles, and small dinosaurs. For this reason, it is very important to not stick with the headlines on the internet, not even a specific or scientific pages. It's important to go straight to the sources, read the details critically, and above all, differentiate the data from the interpretation. Many of the things that scientists affirm do not pretend to be eternal truths, but temporary interpretations of the data that are obtained at a certain moment. If more Beelzebufo fossils are found in the future and new data are obtained, another article could appear with a new interpretation saying that the frogs were actually vegetarians and used their strong bite force to hang from the branches of trees. This is something that happens continuously. As we will see next week, scientific conclusions are always tentative and temporary. I would like to finish with my personal definition of science. For me, science is a wonderful tool to obtain knowledge about nature and about the creator of nature. I am a scientist, and every day I learn new things about God thanks to science. What's more, I think that science was invented by God. When God created the human being, He put in us that innate curiosity that promotes us to ask ourselves the why of things. He also gave us the ability to seek the answers empirically and to analyze them with logic. There are several verses in the Bible that motivate us to test or prove God, to test with our senses and to test God. Find out for yourself how good the Lord is, Psalms 34:8. But like any divine gift, science that is misunderstood or attempted without God's help or guidance can turn into a curse. And let's leave it here, and we'll continue next week with more topics about science.